Right, so in grade 8 we discussed the states of matter. We've got what? Solid. We've got liquid. And we've got gas. Now, in a solid, the particles are sticking together and they are kept in fixed positions. Particles in fixed positions. In liquids, what do the particles do? They slip and slide, so they move a little bit more freely. Particles slip and slide. And in gases, they are free to move apart. So in solids, these particles stick together so strongly that they are in fixed positions, and we can, if we want to, represent them in a model that tells us that they are tied together. These little dashes tells us that these particles are all tied together. Maybe I should draw it in a different color so that you can see it, and maybe I should use arrows and not dashes. So these two particles would be like there's a rope between them keeping them in place, or a bar or a rod or something. Those two will be stuck together like they're attached to each other and they're in fixed positions. Those two are attached together. There isn't a real line joining them, but they are kept together, all of them, in fixed positions. So how would they move? Because, listen carefully, this is very important. Yes.
You see that since you're recording, are you also recording like your voice?
Yes.
Oh,
Now we're moving.
oh, okay.
Temperature, here it comes, is the measure of average kinetic energy. This is a very, 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 very important definition. Temperature is the measure of the average kinetic energy of particles. Okay. Are you listening to what I'm saying, or are you just worried about writing it down? Okay. So, in liquids, these particles can slip and slide. So they are not in fixed positions anymore. They're still clinging together, but they're not in fixed positions. Are you with me? And in gases, these particles will separate completely. They will move apart completely. I've just paid a visit to the little room, and somebody sprayed some air freshener, but that air freshener, if I go again, That I won't smell it anymore. Because it spreads and it moves out and it moves everywhere. You understand what I'm saying? So, who's got the strongest forces between them? Solids got the strongest forces between them. Liquids, the forces are weaker. And in gases, the forces are so weak that the particles can separate completely. So the solids have the strongest forces, where gases have the weakest forces. Okay, now, who's got the more energy?
Oh, the gas.
Yes, weakest forces means the most energy. And energy here is the energy of motion that we call kinetic energy. And who's got the least kinetic energy? The least energy of motion. Yes, this has got the lowest or the least kinetic energy, and I'm using an EK, E for energy, K for kinetic.
Ma'am,
Yes,
how would you describe the energy that the liquid has?
it's in between. And the forces in between the weakest and the strongest. Alright. Now this energy and these forces, they determine the properties of solids. What can we say about solids? They keep their shape. Can you compress a solid? No, they're incompressible. Can diffusion take place in a solid? No, because the spaces between solid particles are too small. Okay. Liquids. What can we say about the forces? It's weaker. What about the spaces? It's bigger. Can you compress liquids? A little bit. Can liquids expand? Yes, if you heat it up, it will expand. Solids as well, if you heat it up, it can expand. Can diffusion take place in solids? Yes, we did that for potassium permanganate. Yes, in a liquid, in liquids, yes. Things can mix. Otherwise, your coffee, you won't make coffee. You can't make tea. If diffusion doesn't take place in the liquid, then the coffee will stay at the bottom of the cup. The tea will stay at the bottom of the cup. It won't mix to have one color. Pardon?
It's usually when you speak about diffusion, it's usually we think about gas, right?
But also in liquids.
Before it's
Diffusion
diffusion.
is when one substance mixes into another substance from a high concentration to low concentration. And in gases, the particles are so far apart that diffusion takes place fast. They can be compressed. We can move through them easily. So the properties of gases are determined by the forces and the energy of a gas. The properties of liquids are determined by the forces and the energy of the liquid. The property of a solid is determined by the strength of the forces and the energy of the particles. You got it? Now, I want us to look at what will happen during a phase change.
So particles have phase. Like, are some
Pardon?
particles- Is it possible for one particle to be in phase with another?
No, you are talking about another in phase. You are talking about waves. I'm off the physics now. Okay. before we go to phase change, I'm going to represent only a solid first. And let's make it real. Let's look at ice. Okay, so ice is H2O S. It's a solid. Okay? Now, in ice, your particles are in fixed positions. Please look and learn now. Please stop copying. You can make your notes. Your textbook is quite sufficient. Okay? I'm drawing them far apart because I want to work between the particles. What keeps the particles together? Forces of attraction. So there are forces of attraction that keeps particles together. But, oh, my good question is, what causes these forces of attraction? What do you have in the particles?
Is it charges?
Charges. Which ones are? Electrons that are negatively charged and positively charged causes the protons. Okay, so those things causes attraction. But they also cause repulsion. So these two particles will also have repulsion. Because like charges repel, am I right? Like charges repel, unlike charges attract. So you have both these forces acting between the particles, attraction and repulsion. So what happens is they want to move together, but the repulsion gets too strong. So all they do is this. And what can you call a motion like this? Yes. And a to and fro motion is called a vibration. So in solids, the particles vibrate. They vibrate around their fixed positions. So what energy do they have because of the vibration? High kinetic energy. So they do have energy of motion. Am I right? But they have another energy as well. What keeps me to the floor?
Gravity.
A force of gravity, a force of attraction. Okay. So a force of attraction keeps me to the ground. What if I get onto the step ladder? What energy will I gain if I get onto the step ladder? Yes? Potential energy. So the further I am from the floor, the more potential energy I will have. You got me?
Yes.
Alright. So don't you think these particles will have potential energy as well? Because if they go further apart, those forces of the potential energy will increase. Yeah? You need to be able to visualize this. The further away you go from the Earth's surface, the bigger your potential energy will be. The further away the particles go from each other, the bigger their potential energy is. Now I'm going to tell you the secret to phase change. So particles have both kinetic energy and potential energy.
Is this just for the solid?
For any particle. I'm just starting with the solid. Kinetic energy, I can use the symbol EK. Potential energy, I can use the symbol EP. You might find some textbooks uses K and U, but I'm not used to that, so I prefer EK and EP. Makes more sense to me. Okay. So these particles, because of the motion, they have kinetic energy, and because of their position, they have potential energy. Now what will happen if we heat the solid?
They gain energy.
Wait, just think.
They gain
Just
energy.
think. Just think. Just think first. Okay? What will happen? Think about it. In terms of the energy, what will happen if I start heating the ice?
The vibrations will increase. The ice. They'll change matter.
Heating ice. What will happen?
They'll change. Like the phase change.
Say we've got ice at minus 14 degrees Celsius. What is the melting point?
0 1 degree.
The melting point of water is 0 degrees Celsius. So what we're busy doing is we take this ice and we heat it up a little bit. Shall I heat it up a bit?
Yes.
Okay. So I take it and I put it on that stove plate. So the heat energy goes there. Are you visualizing it?
Yes.
So these particles will increase in temperature. You remember I said temperature is the measurement of average kinetic energy. So if you heat the ice, the temperature will increase. What else will increase? Kinetic energy will increase. Now, wait now. Will the position of the particles change while the ice is still solid?
No.
So, what will happen to the potential energy? The positional energy.
Will it decrease now?
Now, wait a moment. My first question was, will the position of the molecules change while the ice is still solid? No. So you are answering me correctly. So now I want to know what will happen to the positional energy. Remains
the same. The same. The same.
the same.
Yes.
Okay? The potential energy will not change while you've still got ice, and you can have ice from minus 14 degrees Celsius to 0 degrees Celsius. You can have ice. Now here, so that will be the solid ice. You will see that once the ice gets to 0 degrees Celsius and you continue heating it, the temperature will remain constant. It is a secret. Don't tell the rest of the world. So,
And can you please repeat the secret?
The secret formula.
the moment the ice gets to a temperature of 0 degrees Celsius, it turns into a liquid. L stands for liquid. So here we will have at 0 degrees Celsius, we'll have the solid changing into the liquid. What do we call that? It's a phase change, and it's called melting. Do we continue heating the ice? Yes, we continue heating the ice. Now, what will happen to the temperature?
It'll increase.
It'll remain the same.
This is the secret. The temperature will remain constant while you have ice busy melting. While there is ice at 0 degrees Celsius, it will turn into a liquid. The temperature stays 0 degrees Celsius. Tendu. So what can you tell me about the kinetic energy? What is the marriage between kinetic energy and temperature?
Huh? No, the temperature is measured on average of the kinetic.
The temperature is the measure of the average kinetic energy. So if the temperature is going to stay 0 degrees Celsius, then the kinetic energy stays constant. While, listen carefully, while there is a phase change, the temperature stays constant. You're still busy adding heat. You're still busy heating it, but the particles will now be much further apart. Okay? They will spread out a little bit. Okay? If they're further apart, what happens? Which energy is changing? Further apart, the particles moves further apart. So what will happen to that energy of position? Potential energy will increase. So this heat changes into potential energy. This heat is taken by the particles and it increases the potential energy. These particles will move further apart. What happens to the forces between the particles? Are you with me? If you need to stand up to stay awake, do so. Okay. So listen to a summary quickly. If you take ice, that is at minus 14 degrees Celsius, because that's what my deep freeze is set to, minus 14. If you take that ice and you heat it slowly, it will heat up to 0 degrees Celsius. But it will stay solid ice. So the kinetic energy will increase a little bit, but the potential energy, the energy of position, stays the same because those particles are in fixed positions. Okay? Once you get to 0 degrees Celsius, which is the melting point of ice, the ice will start turning into a liquid. The temperature stays constant. So the temperature will stay at 0. What happens to the kinetic energy? It will stay constant. Temperature is the measure of average kinetic energy. What happens? These particles separate further so that they can move from solid to liquid. So if they move further apart, it's like you moving further apart from the Earth. Which energy changes? Potential energy. And what happens to the forces between the particles? It weakens. Let's see if you really understand what I'm trying to say. So we have all the ice now. It's turned into a liquid. All the ice is turned into a liquid. You carry on. Now you've got water. You've got liquid. You carry on heating it. You see? You carry on heating it.
That ice still heating at the same temperature.
No, my dear. Now it's not 0 degrees anymore. All the ice is gone. Now, you carry on heating it. What will happen to the temperature?
It will increase. It will increase.
You carry on heating it. The particles are now all in the liquid phase. They're far apart. Okay, further apart. Not in the gas phase yet. Okay, so we're in the liquid phase now. Can take that out as well. So we've got liquid water. We carry on heating it. What happens to the temperature? The temperature will increase. The temperature will increase. What happens to the kinetic energy? It will increase. What does it mean? You will not put your finger into that water because it will burn you as the temperature rises because you're heating it. What will happen to the spaces between the particles in the liquid phase? More or less the same. The potential energy will remain the same. So the spaces between the liquid particles remains the same. Up to which temperature will this happen? Up to 100 degrees Celsius. The moment you hit the boiling point of water, which is 100 degrees Celsius, you get another phase change. Okay, the liquid turns into a gas. So, what will happen to the liquid's temperature while it is boiling? You don't understand the secret of phase change yet. It's the magic of creation, grade 10s, that the moment the substance gets to a phase change, when it hits that melting point or that boiling point, you can carry on heating it. The temperature you will measure with the thermometer will stay the same. So temperature stays constant. What will kinetic energy of the particles do?
Constant.
It will remain
Constant.
constant. That is, their energy of motion will stay constant. What will the particles do? If they go from liquid to gas, what happens? They move further apart. So the spaces between them becomes bigger. Which energy is busy changing if that happens?
Potential.
Potential energy increases. If the potential energy increases, what happens to the forces?
They become weaker.
Weaker. So in a nutshell, I've tried to explain to you about the energy and the forces and the spaces during phase change. If there's no phase change, the spaces stays the same, but the temperature goes up. If there's a phase change, the spaces increase. If it's absorbing heat, spaces increases, and your kinetic energy will stay constant. It's the secret. During a phase change, temperature remains constant. Okay, just to end off this video, what is melting point's definition?
The point in which.
You can't say the point.
The phase.
It is the temperature at which the solid phase and the liquid phase of a substance is in equilibrium. Now that is a new concept to you. You don't know it. But it means that at 0 degrees Celsius, your liquid water can change into solid water, but the solid water can in the same time change back into liquid water. Yes. So the reaction can go from liquid to solid and from solid to liquid at 0 degrees Celsius. It means equilibrium. At 100 degrees Celsius, that was the melting point. Nah? At 100 degrees Celsius, we've got the liquid and the gas in equilibrium. But that's not the definition of boiling point. Okay. So at 100 degrees Celsius, you can get the liquid to evaporate, but you can also, Sibonga, you can also have the gas condensing at 100 degrees Celsius. Shall I reveal the boiling point's definition? Okay. So boiling point. Now, tell you this story. My brother lives in Pretoria, and my mom and I, for many years, my mom and I went to visit them there in the winter holidays. Horrible. Everything is brown and bleak. You make coffee, but the coffee is cold. You pour the boiling water, but immediately it's cold. Why? What's different? Up in Pretoria, your atmospheric pressure
I think you're above sea level.
Yes, your atmospheric pressure is less in Pretoria. Now, watch the kettle or the pot boiling the water.
Takes longer.
Wait. Small bubbles starts forming at the bottom of the pot when you boil the water in the pot or in the kettle. Small bubbles. What happens to those bubbles? They disappear. They don't come up to the top of the... So, while that is happening, the water is not boiling. Once those big bubbles form and they come up to the top and it's like splattering and spitting out water, that's when the water is boiling. Now, can you remember what is in that bubble?
Oh, it's effervescent.
What is in the bubble of boiling water? Taking you 2 years back.
It's the air.
What is in the bubble of boiling water? Where does the oxygen come from?
Because it must be enough, right?
There's not so much oxygen in that water. It's water vapor. Not air, not oxygen, water vapor. So, listen carefully. Boiling point is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. So once those big bubbles form, those bubbles are full of water vapor, and the pressure in that bubble equals the pressure of the atmosphere on the liquid. So in Pretoria, the air pressure, the atmospheric pressure is less than here. So here the water boils at 100 degrees Celsius, but there it boils at 95 degrees Celsius. Sometimes less, depending where you are. So, boiling point is the temperature at which the vapor pressure of the substance equals the atmospheric pressure on the liquid. These two definitions will follow you into 2025. They are very important. And don't tell me it is the point. No, it is the temperature.